Hello everyone. This is week 3 of the NPTEL course, Nonlinear and Adaptive Control. And this is the live discussions, but unfortunately nobody joined today. So I would be doing some out of the box kind of structure over here. So for example, I would be covering some concepts related to projection operator, and I may go beyond what was taught in the class. So you may grasp a wider understanding of what's adaptive control and how you apply to solve real world challenges. So without further ado, let me switch to my notes app, and I would be discussing some pertinent concepts, so which you may have already covered in the class, but I would be adding some insights onto it or some intuition behind it. So from the next week, I expect some of you to join so that we may have more productive doubt clearing sessions, not just going beyond what was taught in the class. So without further ado, let me switch to my notes app and we would continue. So as you can see my screen, I'm so uh, we would be talking about projection operator specifically because it is widely used in the adaptive control literature, the concept of projection operator. Now, the material I would be taking up in this live discussion can be found from this seminal paper by Levretsky and al. So this is paper by Levretsky. Which is titled Projection Operator in Adaptive Systems. So yeah, sorry for the delay. I'm back. So uh, in general, there is this thing called projection operator, which takes in as an input three things. So the first thing is the parameter which you want to learn, the update law, unprojected, and a convex function which denotes whether the projected quantity is within a user defined bound or not. So this is usually a convex function. Now by convexity, we mean to say uh, a function whose second derivative is always positive. So the second derivative of a function, when it is always positive in its entire domain, then the function is called a convex function, right? So this kind of projection operator takes these three as an input and it produces a projected update law such that theta t is bounded. So, in other words, let's look at some examples, and this would be clearer, hopefully, on those settings. So, for example, let's say I have a parameter theta which is updated by this law of, let's say, tan theta t. In other words, if you plot the update law for theta or the variation of theta with respect to time, suppose I am starting theta from some value, then the theta would grow exponentially with a value. Let's say this is theta naught. Then this would be growing exponentially with theta along this line, right? So if you look at theta versus t, this would be varying exponentially with respect to time. But we don't want that, right? We don't want our theta to be unbounded. So if I had placed the theta dot as projection with respect to theta, and tan theta t was my unprojected update law, and a function such that my a convex function such that uh, when theta is less than some bound, let's say I call that beta, then this function, whatever function I'm choosing, would be negative. But if theta was greater than some bound, then f theta would be positive. So such a function can be chosen as, let's say, theta square minus beta square, right? Because if you look at theta, sorry, f theta, if theta square is greater than beta square, this thing is positive, and it is less than 0 otherwise. So I have this function theta square minus beta square, right? Now, if you look at the projection operator, and mind you, this is obtained from this paper. If you look at the projection, it is simply y minus gradient of f theta, sorry, gradient of f theta transpose divided by a normalizing term multiplied by y into f theta, where let me just scooch this over, and if f theta is greater than 0 and y transpose f, sorry, y transpose gradient of f theta is greater than 0. And it is y otherwise. So let's look at this projection law in for this case of this trivial example. So let's first compute the gradient of f. So when I compute the gradient of f with respect to theta, so this is gradient of f theta with respect to theta, it is nothing but 2 into theta, because this theta being a vector, right? So uh, theta square minus beta square. If I partial differentiate with respect to theta, this is essentially taking a scalar divided by this vector. Sorry, not divided, but differentiation with respect to this vector. Oh, sorry, I misspoke. This entire thing is a scalar because we have considered a scalar case over here. So we would look at an example which is having a vector case. So, but for now we have the scalar value over here, 2 theta. So yeah, let's take this entire projection definition and copy it over here. And I take everywhere where there is gradient of f theta and I replace those by their corresponding values. So I had this and I have this. Right? Now let's focus on what this entire condition is saying. So if theta square minus beta square is greater than 0, then it means that theta is greater than beta. And this condition such that y transpose or y theta 2y theta is greater than 0. This means that theta if theta is positive and correspondingly y is also positive, then this condition holds. So let's draw a truth table for this condition. So this condition is y and is y theta greater than 0. So if y is positive and theta is positive, then it is true that y theta is greater than 0. If y is positive but theta is negative, then it is false. And similarly, if y is negative and theta is positive, then it is false. And if both are negative, then it is true. In other words, if I am currently, let's say this is the overall bound for theta. So let me redraw this over here again. I have this theta over here. And I have this line, which is positive beta and negative beta, respectively. Right. Now, this condition says, so the first condition is that theta must be greater than beta. So it's or theta must be greater than beta, or theta must be less than minus beta. So there are two conditions over here. So it's either here or here, right? So if that is the case, then we have to look at how the theta is changing. So theta dot, how it is changing in the unconstrained setting. So if theta dot, which is essentially the y over here, if it is positive, I mean, it is going, if it is here and it's going above, so y is increasing, sorry, y is positive, and theta is also positive, then we need to apply some intervention, right? So we need to make sure that this theta is becoming bounded to this positive beta line. And similarly, if I have theta over here and y is negative, then I need to apply some intervention so that this theta goes into this bound, right? But suppose if this was the case that theta was positive over here, but the y is negative, then we need not apply any intervention because the unconstrained y would manage to bring theta down to this bounded line. And similarly, the opposite is the true over here, positive, and if theta is negative, then it would be going down here. So this condition encompasses how much you want to project, or in which cases you want to project and in which cases you don't want to project. So in this toy example, these two terms get cancelled out and you are left with this condition. So if you have to project then the projection becomes like this. So essentially, this quantity is positive because one of the condition over here is theta square minus beta square. So this is positive. So this is positive. So this essentially is a negative quantity. Oh, sorry, I misspoke. It essentially becomes y 1 minus theta square minus beta square plus beta square. So depending on the value of y, this projection would change. So if it is positive, it would become negative, and if it is negative, it would become positive. So this is essentially the projection which is applied for this very simple toy example. Now let's look at a complex example and how this thing is done in practice. So suppose in the vector case, I have some theta hat dot, let's say theta hat dot is some gamma times. Let's not focus on the gamma first. Let me consider this to be some minus theta plus I'm thinking of an example on the fly here. Give me a second, please. So let's keep it simple and consider this to be theta as well. But here theta is an n-dimensional vector, right? So theta being an n-dimensional vector, is useful to us owing to the fact that we now consider that theta, the norm of theta, should be less than some beta, right? So we consider the convex function, which is theta transpose theta minus beta square, right? And we could do the similar analysis wherein we would have this kind of structure again, and the projection operator would ensure that the system, the theta is bounded. So this was all about the projection operator. Now, let me describe one property which makes the projection operator, the analysis specifically, easier, the Lyapunov analysis easier. So this is adapted from this uh, seminal paper, and you can observe the proof in the lemma 8 of this paper. Of Leveretsky and all, which says that suppose the projection of theta, y, and f is done, then theta minus theta hat so you are projecting y to theta hat such that theta hat follows this relation, right? And if theta is the original unknown parameter, and theta hat is the estimate, then theta hat minus theta transpose the projection theta hat y and f is negative. So this is very interesting concept because oftentimes in Lyapunov analysis we consider this theta tilde theta tilde as a candidate Lyapunov function. So we have a Lyapunov function on theta, which is theta tilde transpose theta tilde. So half of it, let's say. When you compute the time derivative, it essentially boils down to theta tilde transpose theta hat dot with the minus sign, right? Now, theta tilde is often defined as theta minus theta hat, and thus theta tilde negative would be theta hat minus theta. So essentially, if theta hat dot is some projection of something, right? This entire thing boils down to theta hat minus theta transpose projection of something. Now this is essentially less than 0. So without even computing any cases, so without any going into these two cases, you can easily write this entire thing in one line. So this is a very useful property of projections, and hence projections are very widely used in the adaptive control literature. So let's switch gears a bit and look at an overall higher level picture on how adaptive control is used in other forms of literature. So this hasn't been covered in your course, but I thought it would be a good exercise to look at neural networks and their role in adaptive control. So before I do that, let me just give me 1 second. Hi, sorry about that. So we were talking about neural networks and why they are useful in the sense of adaptive control. Now, you might have studied this Euler-Lagrange system dynamics in the class, right? So you had this kind of structure, right? So this kind of structure is called the Euler-Lagrange dynamics, right? Now, as you have seen in the earlier lectures, that this is often times referred to in the linear in parameter form, right? So you have some parameter, unknown parameter theta, and a regressor. So the regressor was a function of the states and theta was an unknown parameter. So you had linearly separated the unknowns from the knowns, right? So you have this as known and this was unknown, right? Now suppose this kind of parameterization for an unknown dynamics or unknown system was not possible. So for example, I have a very simple case of, let's say, x dot is equal to some function on x and theta plus u, right? So for an example, I can write, hello, I think I'm back. Uh, I hope you can see my screen now. So we had some theta 1, theta 2 parameter, and this can be, let's say, x1 plus x2 plus some u, right? So if you look at this system, here the states is x1 and x2, and the unknown parameter is theta 1, theta 2, theta 3. Right? Now, look at this specific term over here. This specific term has theta 3 and x1 multiplied together. So if this was the case, so theta 3 multiplied by x1 was the case, then you could have easily separated this entire thing out by writing x1, x2, and x1. I would be writing this out and it would be clear in a second. Multiplied by, so the first thing was sine of theta 1. Now I have considered sine theta 1 to be the parameter, the new parameter, and then it would be theta 2 and theta 3 with this bias term 1. So if you look at this multiplication and this multiplication without this pesky sine term, this would have been equivalent. But since I have this pesky sine term over here, I can't easily separate out theta 3 and x1 or some other combination of that, right? So this is called nonlinear in parameter system. Nonlinear non-linear in parameter system, right? So how do we deal with these kind of systems? So this is an extension of adaptive control for these like higher level parameter systems. So I would be teaching you neural networks as a method to solve these nonlinear in parameter systems. Now, to give you a brief introduction to neural networks and what are they, let's look at a general case where I have some inputs. So in this case, in this particular case, I have some function which I want to represent by x and the parameter theta, right? So I have some function which I want to transform from Rn to, let's say, a new domain Rm, right? So n dimensional vector to an m dimensional vector. So I consider n inputs over here, and consequently I consider m outputs over here. So n inputs and m outputs, right? So let's look at a very simple case where I have some connections to these nodes without anything in between. So I would be discussing something in between. But for now, let's consider a very simple example. and I'm just focusing on this particular node over here. So let's just look at this node over here in a detail. So you have this node which is outputting some variable. Let's not look, let's not delve deep into what it is outputting for now, but let's look at what it is having as inputs. So let me give you a concrete example, and then we would be extrapolating it onto multidimensional cases. So let's say I have some inputs x1, x2, and x3, which are coming into this node. Now, what neural networks or per se neurons do is they take some weights, which are W1, W2, W3, which are nothing but parameters. So we had these kind of parameters over here, right? So theta was an unknown parameter. So we have these unknown parameters, which are nothing but weights. So by weights, I mean I take each of the input and I multiply them with the weight, corresponding weight, and I add them together. So W2 into X2 and W3 into X3. And what neural network does is it passes it through an activation function. So activation function is a nonlinear function. Let's denote it by sigma. What it does is essentially takes a single dimensional input. Let's say I call this A, and it finds sigma of A, which can be anything like this or something like this. These are various functions which are used in the neural network literature, which take the real number output from the A, or essentially the multiplication and addition of this entire thing, which is called as A, and it is passing it through an activation function, which is squishing it down to some manageable range, let's say from -1 to 1 or some 0 to 1 range or something else. Right? There are many other kinds of activation functions. So I'm speaking it in very loose terms that this activation function is a nonlinear function simply. Right? So in essence, you are computing sigma multiplied by some weight transpose into x, where x is x1, x2, x3, and w is weight 1, weight 2, weight 3. Right? So this nonlinearity over here is very powerful because it has been shown in neural network literature that stacking these nonlinearities together one after other enables us to learn any kind of function known to universe. So neural networks are known oftentimes as arbitrary function approximators or universal function approximators. Right? So now I said neural networks, right? So what I have shown you currently is one such neuron. So this is a neuron. So how do we call it a network? It's nothing but a stacking of neurons together. So we had an n-dimensional input and we have an m-dimensional output. Let's insert one more layer. These are called layers, which has, let's say, L dimensions or L neurons, right? So if you look at this network, each of these neurons has these kind of connections over here. And so on. Each of these neurons have all possible connections to the input, the layer behind it. And similarly, each of these nodes in the output layer has connections to all of these L layer, the previous layer nodes. And in essence, you can create a very big neural network out of it. And each of these layers has a activation sigma associated with it. These sigmas can be same or different, whatever, right? So in essence, you have from this node, this layer to this layer transformation, you can encapsulate it by saying sigma into, let's say, V transpose X, and from this layer to this layer, you can write W transpose sigma and then again sigma. So in essence, V transpose X is the result up to here before the neural layer node 1, and after that you have sigma of V transpose X, which is then again multiplied by some other W. It becomes W transpose sigma of V transpose X, and then the output is sigma of W transpose sigma V transpose X. And you can stack these up as many layers as you like. So the complexity would be increasing, obviously, but the power of the neural networks come when you stack multiple of these layers together. So how many you stack is completely dependent upon you, and how many neurons you connect is completely upon you. So this is a general purpose representation of a neural network, or specifically the mathematical representation of a neural network. Now, oftentimes in the control or adaptive control perspective, the output layer doesn't have a neural activation function. So, in general, adaptive control you use this so-called two-layer neural network with W transpose and V transpose being the parameters. So let's look at an example, and we would figure out how to like learn adaptive control from very difficult for very difficult systems. So in order to do so, give me 2 seconds. Let me think of an example and then I will come back. So hi, I'm back. So let's look at a very simple case where I have x dot is equal to right. So the first thing you do is you figure out what are your inputs and your outputs. So in essence, this is a two-dimensional system. The state space is two-dimensional. Uh, for simplicity's sake, let me remove the first dimension completely and remove this dependence on this extra state over here, and I can simply remove everything else. This is your simple state equation, right? But however, the challenge is that you can't actually separate these unknown parameters theta 1 and theta 2 out of your expression for your uh, you can't express it in the form of yx multiplied by theta, where yx is a regressor on x, the state x. So you can't actually do that because the theta is deeply entrenched into this nonlinearity. So what we do is we create a neural network. Now the structure of the neural network would take in as input the single state x, and you have some n L number of layer neurons over here in the second layer, and the output would be this representation f. So the output would be this representation f. Now you have some connections for each of these nodes, and out comes this kind of structure. Now we write x dot as W transpose sigma V transpose x plus some epsilon, and I would be explaining epsilon in a bit, plus this u, right? So now let's look at what are the dimensions of these parameters v and w. So v is essentially a 1 cross L matrix, because your state X is one dimensional, and when you transpose a 1 cross L matrix, it becomes L cross 1. So it becomes, this entire thing becomes L cross 1, and sigma operates on each element of this L cross 1 matrix and produces an L cross 1 up to here. And consequently, this uh, W transpose should have this 1 cross L type of structure. This implies W, the dimensions of it must be L cross 1. So the dimensions of W is L cross 1, and the dimension of V is 1 cross L. Right? Now, I talked about this term epsilon over here. So what is epsilon? Now, whatever neural network you choose, you can't exactly exactly figure out what is the parameterization for your system, because there is some nonlinearity still left, and no neural network is absolutely perfect. So to encapsulate that, we consider that there is a function reconstruction error which is epsilon of x. So epsilon is nothing but a vector from Rn to R, right? But since n is currently 1, so it is simply a mapping from R to R. Now, let's look at the system once again. X dot is equal to W transpose sigma V transpose into X. Now, we would consider a very simple case where the first layer is assumed to be fixed. Why do we do that? We just want this second layer to be learned, and the first layer is the weights are initialized randomly. So this is randomly initialized, and it is held to be fixed. Just for simplicity's sake, we are making this as the case. There are other uh, results which we won't go in, where you learn both W and V respectively. Right? So let's say that V is given to you, uh, or you choose it on your own. Right? So the only unknown is this W thing over here. Right? Now suppose you had the exact knowledge of this W. So what you would have done is you would have created the update law or the control U as minus W transpose sigma V transpose X with a minus sign of K into X, where K is a gain, right? So in essence, you would have made sure that this is Kx plus epsilon X. Now, in general, for neural networks with very high number of neurons, this epsilon of X is bounded by some epsilon bar for all x in some compact set D, which is a subset of R. Now this is known as the neural network approximation lemma, which states that for properly chosen activation functions and large number of neurons, any function can be approximated by a neural network such that the function reconstruction error is bounded in some compact set. Right? So this is a lemma which is very famous in the machine learning community, and we use it in the adaptive control community as well. So this bound, establishing this bound, you can choose a k in such a way that this entire result, this x dot thing, is uniformly bounded, uniformly ultimately bounded. Right? Now, I'm not focusing entirely on what if this W was known. So let's look at what if means the actual case where W is not known. And you estimate it by some time varying parameter W hat. Right? So this is the estimate. So when that happens, the estimated dynamics is, or the control law, estimated control law is minus W hat transpose sigma of V transpose X minus K into R. Not R, sorry, X. Minus K into X. Right? Now, for simplicity's sake, I would be referring phi of X as the sigma V transpose X. Right? So in essence, we have X dot is equal to this W transpose phi of X plus epsilon of X plus U, and this U is essentially minus W hat transpose of phi of X minus K into X. Right? Now, what we need to do is we need to design a control law, or sorry, adaptive law for W hat dot of T. We have to design it in such a way that W hat approaches W and X approaches 0 as T tends to infinity. And even if we are not managing to do that, at least W hat should be bounded. W tilde should be bounded, which is defined as, let's say, W minus W hat. This should be bounded. And at least X should go to 0. So let's look at how we can do that. So we have X dot under the application of this control law. I'm just copying it over here. And I take this entire thing and I do some notability magic over here. And voila. So this entire thing becomes W tilde transpose phi of x plus epsilon of x minus k into x. Right? Now, let's look at the Lyapunov function, which is based on x and W tilde, which is half x transpose x plus half W tilde transpose gamma inverse W tilde. Right? Now what I do is I compute the derivative, time derivative with respect to, yeah, so time derivative of the Lyapunov function. So it is x transpose x dot, which I substitute from this entire dynamics. So W tilde transpose phi of x plus epsilon of x minus k of x plus half W tilde transpose gamma inverse W tilde dot. So tilde dot. Now this W tilde dot is nothing but minus of W hat dot, because W is constant. Right? So in other words, I have V dot is equal to this entire thing is this, right? Now we need to design this W till hat dot such that this is UUB at least. So what we can say is we can write this minus K x transpose x plus W tilde transpose phi x transpose plus x transpose epsilon minus this W tilde transpose gamma inverse W hat dot. Now, if I design W hat dot to be projection of W hat comma not W hat comma projection of, let's say, let me design it properly. So gamma multiplied by, so the dimension of phi was L cross 1, right? So L cross 1 multiplied by x would be, so the dimension, give me 2 seconds please. Yeah, sorry, I'm back. So the dimension of W was L cross 1 and the phi was also L cross 1. So this entire thing becomes phi into x right. So you need to perform some kind of dimensionality check in this step so as to make sure that the uh, proper dimensions are lining up, and you can easily figure this out later. So when you substitute this kind of adaptive law over here and use the properties of this projection operator, which I talked to you about in a few moments ago, this property, you can see that without having to compute any other cases, I can easily cancel these two terms out. It can be easily done that way. So when this happens, we can write V dot is equal to minus K x transpose x plus x transpose epsilon less than or equal to, right? Now, we can upper bound this quantity by using the Cauchy-Schwarz inequality, and we can write this, the norm of x transpose multiplied by the norm of E, sorry, the epsilon, and this becomes minus K into norm of x squared. So when this happens, we can observe that E, the norm of epsilon, is upper bounded by this quantity epsilon bar. So minus K x squared plus norm of x into epsilon bar. So we can complete the squares by considering k to be common. So minus k is common. I'm taking out common from this side. Norm of x squared with a minus sign of norm of x epsilon by k. And I add and subtract the epsilon bar by k 2k whole squared. Epsilon bar by 2k whole squared. So when I do that, you can easily complete the squares from this and this to write minus k norm of x minus epsilon bar by 2k whole squared with a minus sign of epsilon bar by 2k whole squared. Right? Now we can show oh sorry, I made a huge mistake. So in the completing the squares, you don't extinguish the entire thing. You just rewrite this entire thing. So I'm making so many mistakes today, so pardon my discretion. So what I do is take half of minus this I divide it in two parts, so minus k by 2 minus k by 2 norm of x squared plus norm of x multiplied by e bar. So I complete the squares based on these two, and I keep this intact. So minus k by 2 norm of x square. So this is the problem of doing it everything on the fly, because you made very silly mistakes, and it's embarrassing to say the least. But okay, yeah. So x square minus 2 epsilon bar by k to norm of x, and I add and subtract. So first addition, so epsilon by k whole squared, and subtract epsilon bar by k whole squared. So when you do that, you can easily show that this, I can write this minus k by 2. This entire thing is um, mod norm of x minus epsilon bar by k whole squared, with a minus sign. Yeah, the minus sign. Minus sign epsilon by k whole squared. And when I write this, I mean expand it, so I can write right. Now this quantity is always negative, so I can upper bound that by 0. So I can write minus k by 2 norm of x squared plus k by 2 epsilon bar by k squared. Now this v dot is negative if norm of x is greater than, not is negative, completely negative, if x norm of x is greater than epsilon bar by k, right? Otherwise it is not negative. So if you look at the norm of x plot over time, so if you look at norm of x's plot over time, sorry, if the norm of x is starting from somewhere along these lines, with epsilon bar by k, this is the line over here, it was essentially decay down and reach this epsilon bar by k line. And once that happens, it won't go outside this region. So this is the region where it is converging to. And once it is inside this region, you can't say anything about it. But the only thing you can say is that it is in this region. So this is essentially a uniform ultimate bound of the system. So once you obtain this kind of result, you can show that x and w tilde are bounded ultimately. And uniformly. So this is uniform ultimate boundedness. So to recap, you had a very complicated system which was nothing but a nonlinear in parameter system, right? So you had this system over here which I had considered. Let me find it for you. Yeah, so this was your system. So you had all these cos sine terms, right? And consequently you have this highly nonlinear parameter system. And what you did is you represented the unknown nonlinear in parameter system fx comma theta as this so-called neural network. So you had a two-layer neural network, and the first layer of it was fixed, and you had arbitrarily initialized with some random weights, and you had considered multiple neurons in that layer. And the output layer, which had this weight vector W, not weight vector, but yeah, weight matrix W, multiplied by this sigma of V transpose X. Now, this sigma V transpose X was considered to be this phi of X, right? So, in essence, you had decomposed the nonlinear in parameter system, NLIP system, into this form of W transpose phi of X plus some epsilon X. So this is called a single layer neural network. Single layer neural network. Right? So once you do that, you can easily compute a control law or an adaptive law such that you can figure out whether the states and the neural networks parameter bound are all bounded. So this kind of neural networks are highly used in these adaptive control field, and we could have uh, various different uh, complex functions, and based on this neural network structure you can represent them by these weights and activation functions, and you can compute your control law and adaptive law respectively. So since there aren't any of you, I leave this uh, discussion session up till here. And in the next week, if you have any doubts regarding this lecture or any of the lectures from the previous sessions, we could discuss those. So the next week would be, sorry, this week's Friday, right? So we would be discussing the last session of the course, and I would be taking up a few more examples. So this was completely off the script and completely beyond what Professor Bhasin had covered in the lectures. But this would probably give you higher level ideas on how this is done. And if in the next week, if time permits, I could show you some real life practical simulation results as well, where this adaptive control framework is applied, and we would have some fun doing some kind of programming or something along those lines. So if time permits in the next week, we would take up those. So, but in order to do so, I would request many of you to be present in the next week so that we could have some interesting discussions and some visualizations as well. So on that note, let me stop the recording, and I thank you all for joining this lecture series, and yeah, take care.